Namaste. Remote sensing is just an extension of how we already sense the world around us. Out of our five senses, sight, hearing, and smell allow us to pick up information without actually touching the source. When you see a mountain far away or hear someone's voice over the phone, you are gathering information from a distance. This is exactly the principle behind remote sensing, where we collect data without direct contact. In remote sensing science, we do this using satellites, drones, and special sensors that can observe the Earth. These instruments detect and record signals like sunlight reflected from the forest or heat released from oceans or cities and so on. Just like our eyes depends on light and our ears depends on sound, remote sensing depends on energy, mainly electromagnetic waves. The exciting part is that it goes beyond human vision. It allows us to capture details in invisible regions such as infrared and microwaves, giving us a much deeper way to study and understand our planet. Remote sensing is simply the way we study objects or events from a distance without touching them. Think of how we use our eyes to see faraway mountains. In remote sensing, instead of our eyes, we use instruments called sensors. The sensors collect information about forests, rivers, mountains, or even clouds. For this to happen, energy must travel from the object to the sensor. This energy moves through air or space in the form of electromagnetic radiation, which is just light, heat, or other invisible energy that travels as waves. When these waves reach an object, some of them are reflected, some of them absorbed, and some pass through. The reflected part, like sunlight bouncing off the earth, is what satellites, drones, or aircraft sensors capture. Once captured, the information is recorded and processed by computers. This helps us to know details like size, shape, or even temperature of objects from far away. Just like our brain interprets what our eyes see, remote sensing technology interprets signals from sensors. It is like extending our senses to see and understand the world in a way we normally cannot. Remote sensing is the science and art of acquiring information about material objects or area or phenomenon without coming to physical contact with the objects or area or phenomenon under investigation. Remote sensing is a way of studying the Earth from a distance. It helps us to collect and analyze information without physically touching or taking samples. This can happen from just a few meters above the ground, or from an aircraft flying high in the sky, or from a satellite orbiting far above the Earth. This technology uses instruments like cameras or sensors placed on the ground, on aircrafts or ships, or even on spacecraft. With these tools, we can observe and understand the Earth's surface in powerful new ways. This picture represents overall process of remote sensing. Remote sensing starts with energy from sun reaching the Earth. It hits things like buildings, roads, soil, grass, water, and forests. Some of this energy bounces off or reflects from these surfaces and travels back through the atmosphere. A satellite floating high above collects the reflected energy using its sensors. This information is then sent to ground station using signals. On the ground, computers receive and process these signals. Scientists and experts interpret this data to learn about different areas like health of forest or type of land use or condition of water and so on. So, remote sensing is really about using satellites and computers to study the Earth from far away, helping us to better understand our planet without having to be everywhere at once. The sun is the main source of energy for remote sensing. It sends out energy that combines electric and magnetic fields moving at right angle to each other. This energy travels in waves called electromagnetic waves. These waves move extremely fast at the speed of light, which is about 300 million meters every second. Electromagnetic waves come in many types with different wavelengths, which is the distance between waves. Wavelengths can be measured in meters, centimeters, or even nanometers, which are very tiny lengths. Frequency means how many wave crests pass by in 1 second, and it is measured in hertz. Wavelength and frequency are linked in a special way. When one gets longer, another gets shorter, or they are inversely related. This is shown in the formula C is equal to lambda times f, where C is the speed of light, lambda is the wavelength, and f is the frequency. Knowing this helps us to understand and use electromagnetic waves in remote sensing. Electromagnetic radiation includes different types of waves such as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Only a small part of these waves, called visible spectrum, can be seen by our eyes. This visible spectrum covers light we recognize as colors of the rainbow, from red to violet. Red light has the longest wavelength and violet has the shortest wavelength. Just beyond the visible light is the infrared band or infrared region, which we can't see but is important in remote sensing. Infrared waves reflect strongly from many Earth's features and picked up by the satellite sensors. While many normal cameras capture only visible light, satellite can detect both visible and infrared light also. This helps us to see much more detail about the Earth's surface, helping us to understand things like vegetation, water and land better than with just ordinary photos. Every object around us exhibits a unique reflection pattern based on its chemical composition or physical properties known as spectral signature. Spectral reflectance or spectral signature refers to the proportion of incoming radiation reflected by non-transparent surfaces. The reflectance of objects varies across different wavelengths, allowing their unique spectral signature to help to identify and distinguish them. The spectral reflectance characteristics of various objects can be visualized on this graph, where each feature reflects different amount of energy in specific spectral bands. For instance, longer wavelengths in the visible and near-infrared range are absorbed more by water compared to shorter wavelengths. When it comes to vegetation often reflects similarly in visible wavelengths but can be easily distinguished in the infrared range. Overall, spectral reflectance can vary significantly even for the same type of object, depending on the time of image capture and the location where it belongs to. Barren land typically appears white because it reflects most of energy it receives from the sun, while an object that absorbs all wavelengths appear black in color. Remote sensing platforms are carriers of sensors that capture data about the Earth's surface. These platforms are categorized based on the altitude and operational range: ground-based, airborne or spaceborne platforms. Each serves unique purposes and operates at different scales of Earth observation. Ground-based remote sensing platforms are stationed on or near the Earth's surface. This includes handheld instruments, tripod-mounted devices, or sensors placed on towers or vehicles, etc. These are primarily used for detailed localized studies such as monitoring vegetation, soil moisture, or atmospheric composition. Ground-based platforms are ideal for calibrating and validating data collected from high-altitude platforms, ensuring the accuracy of satellite or aerial observation. These platforms are limited in coverage but provides high resolution and precise data for smaller areas. Airborne platforms involve sensors mounted on aircrafts, drones, or balloons. These operate at altitude ranging from a few hundred meters to several kilometers above the ground. Airborne platforms offer greater flexibility and can capture data over medium-scale areas. They are particularly useful for applications requiring high spatial resolution such as detailed land use mapping, disaster management, or agriculture surveys, and so on. Airborne platforms can be deployed quickly, making them suitable for emergency situations. However, their coverage is smaller compared to satellites, and operations can be weather dependent and logistical challenges may occur. Spaceborne platform consists of sensors mounted on satellites orbiting the Earth. These platforms provide large-scale, repetitive, and consistent data over vast areas. Spaceborne remote sensing is invaluable for global monitoring, including weather forecasting, climate change studies, and resource mapping. Satellites operate in different orbits such as geostationary or polar orbits depending on their mission. While they offer extensive coverage, their spatial resolution or details in the imagery is generally lower compared to airborne or ground-based platforms. Each platform type complements the others, enabling a multi-scale approach to observing and understanding Earth systems. Remote sensing sensors are electronic devices that collect energy reflected or emitted from the Earth's surface. They allow us to study features from a distance without being on the ground. These sensors are of two main types: passive and active. Passive sensors do not produce their own energy. Instead, they rely on sunlight to capture reflections from the Earth. Because they need sunlight, they only work during the day. A camera without a flashlight is a simple example for a passive sensor. It can only take photos when light is available. Active sensors, in contrast, create their own energy to study the surface. They send out beams like radars or laser pulses and measure how much energy is coming back. This helps to reveal distance, surface texture, and material properties. Active sensors work both day and night since they do not depend on natural light. A good example for active sensor is a camera with a flashlight. It creates its own light to capture the image. Together, active and passive sensors give us powerful tools to observe and understand Earth in different conditions. Remote sensing data products are outputs that we get from remote sensing or satellite-based technologies, and they can be divided into two main types: analog data and digital data. Analog data comes from older systems like cameras mounted on balloons or aircraft. They use light-sensitive films. These images could be very detailed, but to use them in modern tools, they first need to be scanned and converted into digital format. Digital data, on the other hand, is collected using digital cameras or sensors that directly store reflected energy as digital values. This allows faster processing and easy use in computer systems. One of the most common examples of digital data is satellite imagery. Satellite sensors that record reflected radiation and convert it into digital numbers, also known as DNs or pixels. Pixels are arranged in a grid to form the full image, and smaller the pixel, higher is the resolution of the satellite image. This makes digital data essential in modern geospatial studies. A pixel or picture element is the smallest unit of a digital image. In remote sensing, each pixel represents a specific area on Earth's surface and stores a single value, which corresponds to the amount of electromagnetic energy recorded by the sensors for that area. These pixels are arranged in a grid to form the complete image. Think of a pixel as a tiny square patch on the ground that the satellite can see and measure. The size of a pixel is directly linked to the level of detail in an image. This size is referred to as the spatial resolution of the image. For instance, in satellite imagery, a pixel size of 30 meter means that each pixel represents a 30 by 30 meter area on the ground. Spatial resolution tells us how much detail an image can show. A 30 meter pixel image can capture small features like buildings, roads, or ponds very clearly, making useful in city planning or farming. A 100-meter pixel image can still show land types like forests or towns, but miss smaller details. With 300-meter pixels, the image is much more coarser, showing only broad patterns like global vegetation or ocean or land, these kind of classifications. In simple terms, small pixel gives sharper details, while larger pixels are better for big area or larger area studies. This makes pixel size is a key factor in remote sensing. Remote sensing satellites are placed in specific orbits around Earth to capture data about its surface. Most of them use what is called a sun-synchronous orbit. This means the satellite passes over the same place at about the same time when it captures imagery. Because the lighting conditions stay nearly the same, the data is easy to compare over time. These satellites usually travel from north to south while Earth spins from west to east. So eventually the entire planet gets covered. They typically fly at heights of around 700 to 800 kilometers above Earth. The sensors on board capture imagery in a strip called swath, which can be tens of hundreds of kilometers wide depending on the sensor's type. On the other hand, communication satellites stay fixed over one spot in a sky using a geostationary orbit, giving constant coverage of that area. Indian Remote Sensing or IRS, a satellite system, was started in the year 1988 to provide valuable data for many applications. Over the years, India has built one of the largest constellation of remote sensing satellites around the world. Satellites like IRS-1C, IRS-1D, IRS-P3, IRS-P4 have been used to capture data in different spectral bands and resolutions, helping in the fields such as agriculture, water management, forestry, urban planning, and even disaster forecasting for floods and droughts. The National Remote Sensing Center, or NRSC, which is a part of ISRO, plays a central role in this program. Its ground station at Shadnagar near Hyderabad receives and processes the data sent by these satellites. India's journey began with the launch of IRS-1A in 1988, followed by IRS-1B in 1991. Later, more advanced satellites like IRS-1C, IRS-1D introduced sensors such as LIS-4, AWIFs, and so on. In 2005, IRS-P5, also called Cartosat-1, provided data for large-scale mapping, and then in 2008, Cartosat-2 brought high-resolution imagery with a camera capable of capturing objects less than a meter wide. The IRS program also includes satellites for ocean monitoring like OceanSat series, making it cornerstone of India's space achievements. Remote sensing is a powerful tool to observe and understand the Earth's surface. By capturing images of natural and human-made features, it can help to monitor, map, and manage resources more effectively. When combined with Geographic Information System or GIS, it has transformed fields like farming, forestry, geology, water, and ocean studies. One important application is in coastal studies, where it helps to track mangroves, coral reefs, and shoreline changes, while also supporting efforts to manage and protect coastal zones. Remote sensing is very important for flood monitoring and management. Satellites capture high-resolution images that help to map flooded areas and quickly identify regions at risk. When this data is combined with geographic information system, this becomes easier to estimate water levels, check damage to roads or buildings, and plan rescue efforts. Remote sensing also provides near real-time information which is critical during floods and cyclones. And this also allows authorities to respond faster, reduce losses, and support people affected by the disasters. Another important use of remote sensing is in land cover and land use mapping. By using data captured over different times, it helps us to see how land changes and how it is being used. We can identify farming areas, forests, or open fields such as urban spaces like housing, markets, or parks, and so on. This kind of information is very useful for city planning, managing resources, and checking how human activities affect the environment. Remote sensing in India is not limited to its own satellites. In 1970s and 80s, India relied on foreign satellites like Landsat, Nova, and Spot for the data. A major step came in 1979 with the setting up of Earth Station in Hyderabad, which allowed India to directly receive Landsat data. Since then, India has continued to use data from international satellites to support its own programs. Today, organizations like National Remote Sensing Center or NRSC acquire data from satellites such as Nova 17, Nova 18, Terra, Aqua, and ERS. These provide valuable information on weather, land cover, and environmental change. National Remote Sensing Center also distributes data from advanced satellites like RadarSat, Iconos, QuickBird, and other commercial images. Using both Indian and foreign satellites ensure there is enough data for projects like disaster management, agriculture, urban planning, and climate studies, and other governmental projects. Integrating these sources allows remote sensing to give a complete picture of the Earth system and support decisions at local and global scales. Thanks for watching. Namaste.